Let's keep studying a reaction like that and changes relationship between the changes in free energy and the equilibrium constant. And from a previous video, we learned that if we know the free energy change, this is related to the equilibrium constant in this way. So E to the delta G over RT, where that's the change in Gibbs free energy, that's the gas constant, and that's the temperature. And now, also, we know our definition about the equilibrium constant being, this is the product of the concentration of these two species over the product of the concentration of A and B. That's. And that we also talk about different scenarios. So say if we have a reaction that is like that, and this is Gibbs free energy, reaction coordinate, this process has a delta G greater than 1, so products greater than reactant, and that's endergonic. We have another scenario in which we can have this. So in this is here, reactions, products, so A, B, C, D, and here reactions, products. Gibbs free energy here, reaction coordinate, that process here is delta G is negative and is exergonic. And finally, we talk about a reaction in which then about the same Gibbs free energy in reactions and products. So if this is G and this is, that wasn't straight precisely. Well, I'll try. Reaction coordinate. If this is reactant, so A and B, A plus B, and this is product C plus D, here there is about no change in Gibbs free energy. And so we talk about the equation. Say here that it's pretty much no change in Gibbs free energy. What is that in terms of that equation? So if delta G is 0, when we go to the equation above, K of equilibrium will be equal, that's a 0, E to the 0, that is 1. So what I was saying, that if the K of equilibrium is 1, it means that we have K of equilibrium being 1, it means that we have about the same concentration here of the products and the reactions and products. That's what that means. So this is giving you 1, meaning same here down above, down below. This is true. So at the equilibrium, we will have about the same concentration of reactant and product. So now that's not the case when we have other scenarios. So say that I have a number here that difference in Gibbs free energy, let's see, look at the numbers that I have in my table. So when the difference in Gibbs free energy, and that little 0 refers to standard conditions. So if this is negative 17, right? So a very much a negative number, right? So now when you substitute that in the equation, that will give me negative times a negative a positive number. So this is going to be large. So that equilibrium constant for that number is 10 to the 3. Well, that means that I have about 1,000 times more of the products than we have reactants. Oh. Okay, so that, again, 10 to the 3, 1,000 times more products than reactants. That's what it is. So, in that, we can say is about 99.9% products, product favor. That's what that is. So, bearing a negative delta G, and you will have a large positive number, saying a lot of products. So what happens if we have now this delta G? I'm going to pick the same number, but now with a positive sign. So positive 17. Well, that would mean a key of equilibrium of 10 to the negative 3, right? So that's much smaller than 1. So 10 to the 3 is larger than 1. That's much smaller than 1. That you can write as 0.001, right? So we will have the fraction of product is very, very small, and we will have more reactants. So this means reactant favor, and this is product favor. So again, that term spontaneity then refers to reactant favor or product favor. So a negative change in delta G give you a product favor. And here we have the estimation of the equilibrium constant and the amount of products. Here, when that change is positive, then equilibrium constant is smaller than 1. That's a small number. And then the fraction of product that we have here is like 0.1% of products. So most of that will be then shifted, say, the equilibrium to the reactant. So that's the case when the process is endergonic. This is this case. The G greater than 0 is this. So it is reactant favor. See how much product? 0.1. So the rest 99.9 is reactants, which are lower in free energy. This is the other scenario in which you have a negative delta G. That's this number here. So free energy of the product is smaller than that of the reactant, and here you have an equilibrium constant, very large, larger than 1, and then it is product favor by this much. So that's how we can interpret then the relationship of Gibbs free energy and the equilibrium constant. But by looking at inspection of the diagrams, we know that this process, for example, this change is negative. And we also see the Gibbs free energy is lower in the product. So that's product favor. And the opposite here. And this process right here in this picture is neither product favor, not reactant favor. They are in equilibrium at about the same amount.